Hi everyone. Today we're going to study Green's theorem. Let capital C be a positively oriented, piecewise smooth, simple, closed curve. And let capital D be the region enclosed by the curve. Green's theorem states that a line integral around the boundary of the plane region capital D can be computed as the double integral over the region D, where the path integral is traversed anti-clockwise. In symbol, we write like this: the line integral over C, P dx plus Q dy is equal to the double integral over D, partial derivative of q with respect to x minus partial derivative of p with respect to y, d capital A. This is our working formula. Example 1. Use Green's theorem to evaluate line integral xy dx plus x squared y cubed dy, where C is the triangle with vertices 0, 0, 1, 0, 1, 2 with positive orientation. First, let us write the formula of Green's theorem. Now, let us collect the values of P and Q. Let's begin with the P, and we write here xy. This is the function with the dx. Then, we write the Q. We write x squared y cubed. This is the function with dy. Let us now substitute these values in our double integral formula. Now let us evaluate the partial derivative of x squared y cubed with respect to x. And that becomes 2x y cubed minus partial derivative of xy with respect to y. So we write here x. Now let us draw the triangle. The vertices are 0, 0, 1, 0, 1, 2. Take note here that the line which is corresponding to the hypotenuse has the equation y equals 2x. We can get this equation using the two-point form of the line. We can observe here that x is between 0 and 1, while the y is from 0 to 2x. Let us redefine our d of a. We change this to be dy dx. And then let us write the corresponding limits of the double integral. For the first integral, that is for the dx, we write here from 0 to 1. And for the second integral, corresponding to the dy, we write here from 0 to 2x. Let us start doing the integration starting from the inner integral. So we have the integral of 2x y cubed minus x. This is with respect to dy. The integral of 2x y cubed dy is 2x times y raised to 4 all over 4 minus integral of x with respect to y is xy. We will integrate this with respect to 0 and 2x. So this 2 and the 4 can be simplified into 1/2. So we write here x over 2 times the quantity 2x raised to power 4 minus 0 raised to power 4 is simply 0. Minus, for the xy, it becomes x times the quantity 2x minus 0. Simplifying this further, The first group becomes 8x raised to 5 minus 2x squared. Let us now integrate with respect to dx. So the 8x raised to 5 becomes 8 times x raised to 6 over 6 minus the 2x squared becomes 2 times x cubed over 3. We evaluate this from 0 to 1. Take note, this 8 over 6 becomes 4 over 3. So the x raised to 6 becomes 1 raised to 6, which is 1, minus 0 raised to 6, which is 0, minus this 2/3 we write here outside the x cube, and then this x cube becomes 1 cube, which is 1, minus 0 cube, which is 0. The 1 minus 0 is simply 1. We simplify this further into 4 over 3 minus 2 over 3, and the final answer is 2 over 3. Example 2. Use Green's theorem to evaluate line integral the quantity y raised to 4 minus 2y, then dx, minus the quantity 6x minus 4x y cubed, then dy, where C is a rectangle with vertices 0, 0, 6, 0, 6, 4, 0, 4. We write the Green's theorem formula. Let us collect now the values of P and Q respectively. Let's begin with the P. That is the y raised to 4 minus 2y. That is the function with the dx. Then the Q, the negative of the quantity 6x minus 4x y cubed. We include the sign in here. This is the function along with the dy. So we simplify this further into negative 6x plus 4x y cubed. Let us substitute the values in the double integral formula. Let us now evaluate partial derivative of negative 6x plus 4x y cubed with respect to x. And the answer will be negative 6 plus 4y cubed minus partial derivative of y raised to 4 minus 2y. So we have 4y cubed minus 2. If we remove the grouping symbol here, we can combine these two functions into a single and simple one, and that is negative 4. Now let us draw our rectangle. The vertices are 0, 0, 6, 0, 6, 4, 0, 4. We redefine now our double integral formula. The d capital A becomes dy dx, and then let us write the limits of integration. For the first integral here, the outside integral, that is with respect to dx, so the limits are 0 and 6 respectively. For the inner integral, that is with respect to dy, the limits are from 0 to 4. Since negative 4 is a constant, we can move this outside the integral signs. So it becomes like this. Now let's begin our integration with respect to the inner integral, with respect to dy. So we have here the negative 4 times the integral from 0 to 6. The integral of dy is simply y. Then we evaluate this with respect from 0 to 4. We simplify this further into 4 minus 0, and this becomes 4. This 4 is a constant, so we just multiply this with the negative 4 outside. We simplify this further into negative 16 times the integral from 0 to 6 dx. Let us integrate further. The integral of dx is simply x, So we copy the negative 16 here. We evaluate x with respect to the limits of integration from 0 to 6. So the x here becomes 6 minus 0, which is 6. And this 6 is multiplied to negative 16. So we have this negative 96. This is our final answer. I hope you learned something from this video. See you again next time.